We will start Unit 3 with a discussion on work done by a force. When does a force do work? Do all forces do work? Well, no, not all forces do work. You can see I am actually applying a force to hold this in place. But this force is not doing any work. But when I lift it up, I am applying a force and making that force move. Only when a force moves or produces displacement will that force do work. Work is done by a force when it produces a displacement. A force that does not produce displacement will not do any work. Now, very often in our normal language, we distinguish between work and play. Is that right? You know, little children sing work while you work and play while you play. Well, isn't playing working? You hit a tennis ball with a racket. You can see you apply a force and move that force. You're working. The moment you jump up to shoot a ball, when you jump up, you are moving a force equal to your weight. So when I jump up, I'm doing work. So in physics, there is no distinction between working and playing. Whenever a force produces displacement, that force does work. And how do you measure work? Work done by a force is measured as the product of the force and the displacement it produces in the direction of the force. It is very important. If there is no displacement in the direction of the force, then there will be no work done. You remember we did a problem in the last unit. What is the work done by the force of gravity on the moon? The force of gravity does not produce a displacement in the direction in which it is acting. Therefore, it does no work. So work is done only when the force produces a displacement in the direction of that force. Now let's consider a force F applied on a box that is kept on a surface. A force F that is applied on a box produces a displacement. Let's move that box and it comes over here. What is a displacement? The displacement is x. Therefore, what is the work done? Work done is a measure of force multiplied by displacement in the direction of the force. So work equal to F Newton multiplied by x meter. Force multiplied by displacement. That will be F times x Newton meter. The unit of work is a Newton meter and we call that unit a joule. And we write it using the uppercase J. So what is the unit for measuring work? Work is measured in joules and it is a Newton meter. When 1 Newton force produces a displacement by 1 meter, the work done is 1 joule. Now, what happens if the displacement is not exactly in the direction of the force? Now, if you look here, I have a force F that is at an angle theta with the horizontal. And if this force produces a displacement along the horizontal direction, what will be the work done? Will there be any work done? Well, Here, work is done by the component of this force in the direction of motion. Alright, tell me, what is the component of this F in the direction of motion? Well, once you know that, you can calculate the work done. Well, the component of the force in the direction of displacement is the horizontal component of the force, and that will be F cos theta. That means, although there is a force F there, not all that force is doing work. Only the horizontal component of that force produces displacement in the direction of that force. That means only F cos theta does useful work. Therefore, work done in this case will be the F cos theta produces a displacement x. So if the box is now displaced through a distance x, this displacement is produced by this component F cos theta. Therefore, work done will be F cos theta Newton multiplied by x meter. That will be Fx cos theta joules. Is that right? The big J stands for joules. So work done is the product of the component of the force in the direction of displacement and the displacement multiplied. The work done W is F cos theta multiplied by x. Alright? Work is the product of force and the displacement in the direction of motion. Or work is the product of displacement and the force in the direction of displacement. Well, and work done is measured in a unit called joules, which is a Newton meter. The work done by a force can be better understood by studying the dot product of two vectors. Now, we have actually seen how to add vectors. We haven't seen how to multiply vectors yet. Vectors can be multiplied in two distinct ways. We will now look at the meaning of dot product of two vectors. Now look at two vectors, a vector A and a vector B makes an angle theta. The component of vector B in the direction of vector A is B cos theta. Is that right? That means B cos theta and vector A are in the same direction. So, if A and B are two vectors and the angle between them is theta, then the component of B in the direction of A is B cos theta. Now, if you understand that, we can now use this to define the dot product of vectors A and B. And this is how you define the dot product. The product of vector A and the component of B in the direction of A is called the dot product of the two vectors. And we will write it like this: A dot B. That's the way you read it. A dot B. So what is A dot B? A dot B is the product of vector A and the component of B in the direction of vector A. So that will be A times B cos theta. And that is not a vector quantity. You see, A dot B is not a vector quantity. It has just a magnitude. So how do you find the magnitude of this? Multiply the magnitude of A with the magnitude of B in the direction of A. Now this is the way we write magnitude. You see that? We write them in between two lines on the left and two vertical lines on the right, and you read it as norm A. Norm, N-O-R-M. It means the magnitude of A. So A dot B is the magnitude of A times the magnitude of B times cosine of the angle between them. And A dot B is not a vector, it is a scalar quantity. And for that reason, the dot product of two vectors is also called the scalar product of two vectors. So A dot B is a scalar quantity, and its value is the magnitude of vector A multiplied by the magnitude of vector B multiplied by the cosine of the angle between the two vectors. Now that helps us to solve for cos theta. Cos theta equal to A dot B divided by magnitude of vector A times the magnitude of vector B, and that will help us to find that angle theta. Theta equal to cos inverse of A dot B divided by magnitude of A times magnitude of B. Well, there is a very quick way to find the dot product of two vectors once the vectors are given in the component form. For example, let me show you one quickly. If I have a vector A is 4i plus 2j, and vector B is 2i minus 3j. A dot B, remember A dot B is a scalar quantity. Now what you need to do is multiply the x components. 4 times 2 is 8. Now when you multiply, you don't use the i's anymore. Remember, i's and j's are used only for vectors. If a quantity is not a vector, then there is no need for I and j. So multiply the x components. 4 times 2, 8. And then multiply the y components. 2 times negative 3 is negative 6. And simply add them together. So A dot B is 4 times 2, 8 minus 2 times 3. So that will be 2. A dot B has a value 2. Again, A dot B is a scalar quantity. It has only magnitude. So whenever vectors are given in the component form, the dot product can be simply found by multiplying the x components, multiplying the y components, and adding them together. Now watch here, when you multiply the x components, the i's will not come with it. Why? Because the dot product is not a vector. Let's do a problem. If vector A and B represented in the component form, then the dot product of the two vectors is obtained by adding the product of the x components to the product of the y components. Let's do one quickly. A equal to 2i minus 3j, B equal to 5i plus j. What is A dot B? A dot B is, multiply the x components. 5 times 2 is 10. Negative 3 times 1 is negative 3. 10 minus 3 equal to 7. A dot B equal to 7. Well, remember again, it has only magnitude. Now, once you understand